Hello. On the 8th of December 2019, astronomer Edward Guinan at Villanova University reported in the Astronomer's Telegram that the famous red supergiant star Betelgeuse, the shoulder of Orion, had reached a new all-time low in apparent brightness. Guinan's team was particularly interested in Betelgeuse because it is a known supernova progenitor, meaning that at some point it is destined to explode as it ends its life. This dimming that they noticed, and that you can see here in this image, was a small indicator that there was a chance that the star would go supernova. Almost a year later, we found that that wasn't the case. Betelgeuse has increased in brightness again and appears to at least mostly be back to its periodic brightening and dimming. However, if Betelgeuse were to explode, and that's a big if right now. It'll explode sometime in the next 100,000 years, but we don't know exactly when. It would put on a heck of a show. It'd be visible in the daytime for months, and be visible at night for perhaps years. It would be the first supernova from the Milky Way seen with the naked eye since Johannes Kepler's supernova in 1604. But what is a supernova other than a giant explosion? And how have we throughout history, and how do we now observe them? I hope to answer these questions and tell you a little bit more about these magnificent explosions in the heavens. Before you do that, you deserve to know a little bit about me. After all, you need to know who's talking to you if they're going to sound authoritative like I hopefully am. I'm a second-year undergraduate student at UW-Madison. I study astrophysics. I conduct research on two different projects. The first one is at UW-Madison, and that's studying supermassive black holes and the active galactic nuclei, which is when you've got a black hole in the center of a galaxy that's just shooting material from the accretion disk out into space. They're awesome. The other thing that I do is I work with the Pulsar Search Collaboratory, which is a group for high school students to get them interested in astronomy. And I'm leading a project with them that is going to have students studying the Crab pulsar, which is a very rapidly rotating neutron star, which you will see is the aftermath of a massive supernova. So my experience with supernovas, because I study what happens after they're gone. And hopefully that makes me at least a little bit qualified to tell you a bit about them. The only other stuff that you should probably know is that I'm a member of the Madison Astronomical Society, hence why I'm giving this presentation, and that I take pretty pictures of space. You'll get to see a couple more throughout the rest of the presentation. You can see the Pleiades and the Orion Nebula here, both taken by me within the last month or so. So let's get into this. Let's talk a little bit more about supernova. So there are really two types of supernova. The first is a type 1, which occurs when you've got a white dwarf star. A white dwarf star is basically a main sequence star that has stopped nuclear fusion. They're inert. There's not enough heat and pressure and energy for them to continue nuclear fusion. But in some cases, these stars will be in binaries. And in that case, these white dwarfs, these little small stars with about the mass of the sun, can begin to pull material from their twin. And if they pull more and more mass, and they eventually get to about 1.4 solar masses, they reach what's called the Chandrasekhar limit. And at this point, very briefly, nuclear fusion reignites around the star. For a split second, it fuses helium, and then the star explodes in what's known as a type 1a supernova. There's a bunch of other type 1 supernovas, but we're not going to talk too much about them, mainly because I haven't studied them that much. But suffice it to say, there's a bunch of type 1 supernovas that can happen. All of them kind of follow this general principle that you've got a white dwarf and you've got a large star nearby. The white dwarf accretes material. It pulls material from its companion until it reaches this limit and it explodes in a supernova. The other type of supernova we can get is the type that I mentioned with Betelgeuse, a type 2. A type 2 supernova occurs when you've got a massive star, more than 8 times the mass of the sun. Eventually, that star will run out of hydrogen and helium in its core, and it'll begin fusing those elements in kind of an onion out to the exterior of the star. And it'll fuse more and more elements, going up the periodic table from hydrogen to helium, so on and so forth, until it reaches iron. Once iron is fused in the core of the star, well, technically long before that, the star is doomed, but once it reaches iron, it's really doomed. Once it reaches iron, what happens is that there's too much energy needed to make more iron, and not enough energy is produced by the fusion. Once this happens, the crush of gravity wins. There's always this battle between gravity on one hand and the star's fusion on the other, and they usually do a pretty good job of balancing each other. But once that force of fusion is gone, gravity crushes the star inwards, and you get what's called a core collapse. And when this happens, eventually all this matter that gets crushed together has to go somewhere, and it explodes outwards in a massive supernova explosion, what we call a type 2 supernova. To tell the difference between these two things, we look at two things. We look at the spectrum, so what elements are in them. Generally, type 1s do not show hydrogen in them, while type 2 supernova do. That's way number one. And way number two is we look at the light curve. So a light curve basically shows what the light looks like in terms of brightness over time from the supernova. And this graph shows a bunch of different light curves. You can see 1A, 2L, 2P. These are all just slightly different variations of those two classes of supernova. This was particularly in relation to a supernova we'll talk about later, 1987A. But this just kind of shows that over time you see a very rapid brightening, which we'll see later with a great example I found. And then over time, it tapers off. But by judging the light curves and looking at the spectra, we can figure out what type of supernova we're looking at. Now I kind of want us to walk through some historical supernova, because humans have been seeing these things for a very long time, but we didn't really know what they were until the last just really about 150 years. So we begin in ancient China. According to the Book of Later Han, in the year 185, a guest star appeared in the middle of non-moon, which is technically an asterism that contains the star Alpha Centauri, so it's a southern constellation. The size was half a bamboo mat, they said. It displayed various colors. It gradually lessened. And in the 6th month of the succeeding year, it disappeared, was what they wrote. This supernova was the first ever that was definitively shown to be a supernova in the historical record. There are several occurrences of maybes, and maybe they were just kind of stellar nova, which are different, but this was definitely a supernova. We now call this RCW 85, I believe, 85 or 86. And it's visible particularly in radio and X-rays. So this is a predominantly X-ray image from the Chandra Observatory, along with a little bit of radio data sprinkled in, I believe, from the VLA. But this supernova occurred in 185 and is the oldest one that humans have definitely seen and written down. Next, we're going to go to 1006, which sees a massive and incredibly bright supernova. In 1006, we find what is likely the brightest supernova recorded by humans. This is a type 1 supernova from what's actually called a white dwarf merger, which is when you got two white dwarfs, these inert stars that are off the main sequence, and they merge. This is another way that you can get a supernova, because if you merge two stars together that are each about 1 solar mass, and they're all made out of neutrons, that's definitely going to be more than 1.4 solar masses, and you'll get a massive supernova. This one was incredibly bright. It reached a absolute, or not an absolute magnitude, its maximum magnitude, apparent magnitude was -7.5. For you who might be new to astronomy, the larger the negative number is, the brighter the object. So the sun's apparent magnitude is like -26. The moon's is about -12. Every increment of one is about 2.5 times brighter than the next. So if this is -7.5, you can imagine this is, and the moon, the full moon is about -12.5. You can imagine that this is about 100 times dimmer than the moon, but that's still about 60 times brighter than Venus at its maximum. If you've ever seen Venus, it's really bright. This was easily visible in the daytime for months. It was almost visible in the daytime for an entire year, and it was visible at night for several years after it was recorded. Astronomers in the Middle East, in Europe, and in China all wrote about this supernova. Our next one is by far my favorite supernova. It's the Crabby Supernova. It's a bird. It's a plane. It's apparently a crab, because that's what Earl Ross, who's Lord Ross, a famous astronomer, described it as. It looks like a crab. Maybe you see it. I'm not that creative, apparently. I guess you can kind of see it, but this is an image that I took a couple months ago of the Crab Nebula, and it's awesome because this is the supernova remnant that I do work on. So in 1054, a new star was seen by the Chinese, likely the Byzantines, and possibly even some Native American astronomers. This was seen near the constellation of Taurus, which, if you go outside right now, rises in the evening, and you can spot this guy in a small telescope. Like I said, this picture here is my own. I took it about a month ago, and it shows the expanding remnant from the supernova. But importantly, nestled deep inside is a tiny star, about 10 kilometers wide. It's known as the Crab pulsar. And this pulsar spins over 30 times a second. And my research really focuses on what happens to make it really pulse, and what impacts the size of the pulse, the brightness of the pulse. And we do all of this with radio telescopes, which I'll mention a little bit more later. But it's an absolutely beautiful nebula. I hope that you go and take a look at like a Hubble picture, for example. But this just goes to show what you can capture even with my little 4-inch refractor telescope of my own. So next, we're going to fast forward. We're going to skip a couple supernova, and we're going to go to supernova 1572, also known as Tycho's supernova. This was really interesting because this supernova was one of the things that started to poke holes in the Aristotelian view of the universe. So basically, the Aristotelian view of the universe held that everything outside the planets was basically firm and set in place. But when this supernova went off, the Danish astronomer Tycho Brahe noted it, and he wrote an entire book about it called De Nova Stella. In this book, he takes a bunch of measurements of the brightness of the supernova. He tries to do something called taking a parallax measurement. So he tried to go to 2 different places on the planet and see if he could measure an angle between the objects. Because if you're looking at a planet or something, if you go far enough away on Earth, there's a little angle that you can measure to calculate the distance. What he found was that there was no angle regardless of where he went, which meant that this thing had to be really far away, far outside of the solar system, which meant that it was challenging the Aristotelian view that everything outside the solar system was firm and set in place. Tycho's supernova showed some of the first experimental evidence that the universe was much larger than previously thought. And of course, Galileo would eventually show that not only was the universe much larger than we thought, but that the Earth wasn't in the middle, and neither was the sun. So this is really the beginning of the end. This and Copernicus are the beginning of the end for the Aristotelian view of the universe. Now we got to talk about telescopes. Galileo obviously invented the telescope, taking a Dutch invention, eyepiece finder scope, and pointing it upwards. He improved the Dutch models significantly, and his work on uh, understanding the motions of planets and stuff was revolutionary. However, he didn't get the chance to um, ever look at a supernova through his telescope. The most recent supernova was in 1604, just a few years before he built his telescope, so we never got a good look at it. So our first really high quality view of a supernova would occur in 1885, when there was a new star that was barely visible near the core of M31. M31, Messier 31, is also known as the Andromeda Galaxy. It's the closest major galaxy to the Milky Way, and it's on a collision course with us. But remember, in 1885, they didn't know that yet. So when this star showed up near the core of it, people were very surprised. They took measurements, they took spectra of it, but it would not be until close to 40 years later when two people, a man named George Ritchie, who measured a bunch of nova, which are kind of stellar outbursts, realized that the Andromeda Galaxy and the Triangulum Galaxy, two nearby galaxies, were probably not within the Milky Way. And then when Edwin Hubble mathematically showed using Cepheid variables that those were galaxies in and of themselves, that scientists and astronomers really realized that what they'd seen in 1885 wasn't just another nova, but it was some massively bright object, something new, and they called it a supernova. I believe it was in 1933 that the term was first used. It was somewhere in the 1930s. But the supernova 1885A, which you can see the remnant here, this is from, I believe this is a Hubble Space Telescope image. You can check my sources later. But that little tiny dot right there is the supernova remnant, which is right next to the core of M31. And it's an absolutely amazing shot, but it shows the little iron core left over, the iron that's been shot out, which shows up as a dark blot on the rest of the galaxy. But it's an absolutely incredible object that really started to show us that we were dealing with an entirely new phenomenon, which we eventually called the supernova. We're going to fast forward now to the 1930s, which was when an astronomer named Fritz Zwicky, who's Swiss, the Swiss Fritz Zwicky, he was a professor at Caltech and an astronomer, and he pioneered something known as the Palomar supernova search. And throughout the 30s, 40s, and 50s, he led these massive searches to discover supernova. And he basically single-handedly like quintupled or more the number of supernova that were known about. And he would take plates, these pictures that were taken on a photographic plate of galaxies with supernova, and he discovered a whole bunch of them. His work is incredibly important because his plates were used by other astronomers to measure the light curve of a type 1a supernova. You remember I might have mentioned that at the beginning. And the reason a type 1a supernova is so important is that a type 1a supernova can be used to measure the distance to an object, because the light curve from it is pretty standard across all supernova of that type. So that means if you see a type 1a supernova 150 million light years away, you'll still probably be able to figure out that it, one, is a type A supernova, and two, based on the light curve, how much it's been redshifted and a number of other things, you can tell the distance, and more importantly, the dimness, how much dimmer it is than one here. You can tell how far away that galaxy is from us. So type 1a supernova are kind of one of our standard candles to see how far away an object in the universe is. And it was the work of astronomers like Fritz Zwicky that allowed us to measure these supernova and to learn more about just how large the universe was. As we go on through time, we see more and more telescopes of different types being built, particularly radio telescopes. Radio waves are low frequency, and you need a really big telescope to see them. But the wonderful thing is that supernovae glow really brightly in them, and pulsars are really easily imaged in radio. Well, timing is done in radio. I guess you probably image them too if you got a big enough one, but really what's important is that you can time the supernova remnants pulsar, the neutron star of the core that's left over from the supernova explosion. But with the dawn of these radio telescopes, we were able to observe even more supernova. We were able to observe one called Cassia that exploded sometime in the mid to late 1600s and learn tons more about this incredibly bright radio source. But radio telescopes allow us to study everything from the rotation and the pulse strength of pulsars, so we can study their magnetic fields. And eventually they're going to allow us to study gravitational waves using pulsars, waves created by the merging of objects from black holes to neutron stars, all kinds of awesome things, and possibly even the beginning of the universe if we get really lucky. So radio telescopes allow us to get both beautiful images like this one of Cassiopeia A, a very bright radio source in Cassiopeia, and they allow us to study the pulsars that are, and magnetars and just neutron stars in general that are left over from these massive explosions. Next, I want to talk about supernova 1987A because this is the closest supernova that has been seen in modern times. It was visible as about a magnitude 5.8, 5.7 star, so pretty close to magnitude 6, so dim but barely visible to the naked eye as a star in the Large Magellanic Cloud. The Large Magellanic Cloud is a satellite galaxy of the Milky Way that's visible from a little bit of the northern hemisphere and the southern hemisphere. It's near the Tarantula Nebula, which is, I think it's the largest star-forming region in the entire local group of galaxies, but if it's not, it's still absolutely massive. But as you can see, the supernova was as bright as the Tarantula Nebula, where tens of thousands, if not hundreds of thousands of stars are being formed. One explosion is brighter than hundreds of thousands of stars. It's absolutely incredible. But the wonderful thing about this supernova is that it's allowed us to study the propagation of the supernova wave in basically real time. And it's allowed us to study a lot more about what happens right after a supernova on kind of a micro scale that we don't get to see very often. The Hubble Space Telescope has some incredible pictures of it that you can find of the expanding shock wave from it, and I highly encourage that you check it out. But this is a remarkable supernova and the most recent one that's been easily visible on Earth. I want to end by talking about what happens when a supernova immediately explodes and how amateurs help us understand that. So in 2016, an astronomer named Victor Busso, I probably butchered that name, he's an Argentine amateur astronomer, was testing out a new camera with his telescope, and he was aimed his telescope at the galaxy NGC 613, which is a galaxy in the southern hemisphere. But he started taking 20-second exposures to test out his new camera. And what he saw over the next 90 minutes shocked him and the entire astronomical world. Because, as you can see in this GIF, there is an object which appears and gets brighter and brighter over time. And this was the first time that anyone had optically seen a supernova arrive. So we've been able to detect, for example, neutrinos, which are particles emitted from supernova from 1987A, which let us know that it was coming. But this is the first time somebody had just seen the thing get bright. And both amateurs and professionals were incredibly excited by this. Busso went on to get published with a team of other astronomers who conducted observations of this supernova. And it just goes to show that as more and more people get interested in astronomy, you're going to see more and more events like this. Already there are people who are hunting for asteroids and supernova hunting now with just amateur equipment, and they're able to contribute real science from their backyards. That is one of the absolutely marvelous things about the scientific world today, is just how much intertwining there is between the amateurs and the professionals. With that, I guess I just have to say thank you. I hope that you've learned a little bit about supernova, about how we've seen them through time, about how we observe them today. You've gotten to see pictures by the Chandra Observatory, by the Very Large Array in New Mexico, and you've gotten to see some pictures by me. Remember that picture of the Crab Nebula of the supernova remnant? That was just taken a little bit north or south of Madison with my little 4-inch telescope. What you see here is a giant star forming region. I guess we can go back to the beginning of stars. Many of the stars that are inside this nebula are eventually going to one day go supernova, but I get to see them, and you too can see them before they do, just with your own telescope from your own backyard, even depending on where you are. I just hope that you've enjoyed this, and I hope that you've learned a little bit about it. And thank you very much for listening to my talk. By the way, that's Sol Nebula, but thank you very much. If you would like to see my sources, feel free to take a screen cap of this and go through them. I don't think I missed anything, but feel free to get my email from the Monona Terrace, the Moon over Monona Terrace organizers, and I'll be happy to touch base with you if there are any glaring mistakes. Thank you very much, and I hope you've enjoyed my talk.